So let's start. So today I will talk about the Kilonova-catcher, which is the citizen science program from the GROMA collaboration. GROMA means Global Advanced Rapid Networks devoted to multi-messenger addicts. And it is named in the title, tackles multi-messenger events. So even from the violence universe that deals with gravitational waves that you heard during the school. And so why multi-messenger? Because you have association of gravitational wave emission, but also light signature from those violence universe events. And so to that, we can differentiate in three categories. One connected to the merger of death stars, so either neutron star or black hole. The second category that can be a multi-messenger events with gravitational wave is the collapse of a massive star. And the third category is in more a neutron star that is rapidly rotating, and because the geometry can be reconfigured, it can emit also gravitational wave. So far with LIGO Virgo, we have only detect mergers of a neutron star or black hole. And so I will tackle in my talk this first category and the citizen science program attached to the merger of neutron star and black hole. And for that, we might suspect, as I said, light signature from all the wavelengths. And so why it is very important to do multi-messenger astronomy is to understand more the scenario of this compact object collision from the different messenger. And so they are received as in the different step of the scenario. So let me explain. So you have two neutron stars that are going to get there. You have your inspirer of two neutron stars that are going to get closer and closer, and then there will be the collision. So during that sequence, when they go close and close, you have emission of gravitational wave, and in this gravitational wave, you can have access to interesting parameters as the initial masses, but also some indication about the inclination of the system. When the two neutron stars are as close as they will be collide, matter, so they are disformable, and so it will disrupt matter all around. And this matter will create heavy elements, and due to the heat of the environment with radioactive decay, you can't detect the flash from that, the optical emission that we call the kilonova. So after they collide, you have the formation of a new compact object, and it can be either a high massive neutron star or a black hole, and you have the remnants of the matter that will form an accretion disk, torus accretion disk. And so due to a mechanism that we do not understand so well, there will be some neutrino wind that will also will drive the master expert, and you will also have an emission and an optical signature. And so what we tackle in GROMA is this kind of two component. So how matter is expelled during the collision or just before, and and also the matter expelled from the accretion disk. In addition to that, because it is very complex, when you have the formation of the new black hole or neutron star, you have some beam matter ejected under a jet, and they are very relativistic. And so it will create some flash on gamma rays. So it's not optical here, it's more gamma rays. And if the jet is towards Earth, then you can also detect the electromagnetic signatures of gamma rays. And because the jet is going to decelerate from the environment, you will also observe all that we call the afterglow, which is the deceleration of the jet into the environment. So you will have also a light component from gamma ray to radio. So as you see, we have gravitational waves that tell you more about the dynamic of the system, whereas electromagnetic signature will tell you more about how matter is expelled, either on all the direction with the kilonova that I talk about, either on a beaming axis, which is the jet. And so here in my title, it's called Astrophysics. So I try to show you how all the messenger combining together can tell you more about the astrophysical scenario of the neutron star collision, but also it has an impact of cosmology and nuclear physics. I will not go into detail in this talk, but multi-messenger with gravitational waves is very rich because it has an impact of the two other fields. So just to remind, to be sure that I do not lose everyone. So here in grammar, we'll tackle this famous kilonova, that is the witness, the thermal emission due to rapid radioactive decay of freshly elements synthesized in this neutron-rich ejecta. And so kilonova have been observed over the last 10 years, but they have been only candidates, and the only confirmed and very well characterized event have been revealed by gravitational wave in 2017. That's why the science that we tackle is somehow very new, because our reference event, if you want, with neutron star collision with gravitational wave and kilonova is only from 2017. So now I will go to, make a summary about the science that we tackled and this kilonova. What is gamma? So the problem, you understand that we will have tried to find the optical counterpart on gravitational wave event. But the problem with gravitational wave event is that you don't have a very accurate localization over the sky. It will be dozens of degrees, whereas normally telescopes, they observe arc-minute localization. And so you need to have different steps on the strategy to find the optical counterparts. And I forget to say, but these events are transient, which means that the signal from gravitational waves lasts few seconds, up to few seconds, more milliseconds. And the optical signature of this collision lasts about 48 hours for most of the telescopes under the planets. And then you need to have much more sensitive telescopes. And these much more sensitive telescopes, they do not have a wide field of view to try to find this counterpart over the large localization uncertainty. That is why you need to go on different steps. So you receive your gravitational wave, you have a rough localization over the sky, you will need to use different telescopes to scan the search area to say, okay, we have some candidate of kilonova, which is the one connected to gravitational wave. And then you will see, okay, this one cannot be not because it is not a kilonova, it's more a supernova, etc., etc. So we will go to a vetting of these candidates over several days, and then you can use a deep sky telescopes as the one at ESO. So the problem is that when you have a gravitational wave alert, you have this search area when you don't know where to point. And so when you have different individual groups from astronomers, they will point, in fact, to the best probable region. So they will start by, okay, there is a high probability that the gravitational wave is located at this part of the sky. And so the problem is that when you have a gravitational wave alert, all the teams that are not coordinates, they observe the same target on the sky, whereas maybe the gravitational wave source is just a bit shifted. So here our proposition in grammar is to connect and to coordinate all these individual teams so that everyone has assigned a part of the sky to scan, to go into efficiency, and then try to find as soon as possible the optical counterpart to collect all the information from the scenarios that I just tackled before. So coordination of telescopes with a large team from different observers, from different astrophysicists. We are in multi-messenger, so there are also gravitational wave physicists part of, and this is what is made of grammar, so about 50 members from all over the world that decided to put their effort together to tackle this multi-messenger problem and find the optical counterpart of gravitational wave alerts. So GROMA starting in 2018, founded by IJC Lab at Paris-Saclay and Observatoire de la Côte d'Azur. And so it includes 29 groups International, and also APC, IAP, LAL, OCA, IRAP, and LAM here in France. We use a different telescope from 14 countries and in 20 observatories. So this is the networks. We like to say that when the sun never rises on these networks, there are the different telescopes spread all over the world. You can see that there is different type of telescopes. Some are very sensitive, some are less sensitive. As I said, it is to try to cover all the panel that needs to be used for gravitational wave follow-up. So now we go to the point of today, is that even if we have this 25 telescopes in the networks, is not enough to find the counterpart. Well, this is my point of view and members shared in GROMA. So that's why we add the astronomer amateur to participate to our search of the Kilonova counterpart. And so this is a project of Kilonova-catcher. Today, right now, my colleagues from CEA is the leader of that project. And so the idea is to boost GROMA follow-up capability to help us to find some candidates of Kilonova, so gravitational wave counterpart. But also, if we find some candidates, we need to have more and more data within the first 3 days after the gravitational wave alert to determine whether it is a Kilonova or not Kilonova. So the citizen science program started 1 year after the GROMA program, so mostly 2019. And during the last campaign that we have gravitational wave alert, there have been about 40 participants, and they have kind of quite good telescope from 15 centimeter diameter to 30 centimeter. And so right now, currently in December, now we have about a list of 100 amateur. As you can see, the amateur that we have at first is more in France, but we try to spread all the project all around the world. I would like to say that for the amateur also, there is a little issue with the language. Some of the French, for example, they don't speak very well English and vice versa. So that's why with GROMA, we have also a good representation of all the language. So it is nice to also use for that. And here, this is the founder of this citizen science program. He started from the Toulouse idea and says, okay, so why we do not include that into GROMA? And I say yes, and then as I said now, it's Damien that's supervising. So what are doing the amateur in that? So it's exactly the same as a professional of GROMA, which means that when there is a gravitational wave alert, we send them some targeted sources to follow up in the search area. They will point the telescopes, they will give feedback, give the observation feedback to the GROMA system. We will analyze the data for them, which is not the same for the professionals, they do it by themselves. And then we will find if there is a transient interesting that can be the gravitational wave counterpart. The amateur also participate to the vetting, which means that when there is a Kilonova candidate, they can also repoint the telescope, and which happened also last year. So in conclusion of the first 2 years running of GROMA and its citizen science program, we can say that GROMA initiative, there was like nothing 2 years ago, and now we show that its network is working because we have follow-up about 90% of all the alerts sent during those 3 campaigns. So those 3 campaigns was from 2019 to 2020. And so maybe you will tell me, okay, but what is the difference with the other networks? Are there other networks instead of the French leader one? So yes, but they are not enough. They are not as efficient as GROMA in terms of reactivity, because most of the groups, internationals, they follow up about 5 alerts to 10 alerts maximum during the 3. And here we are about 50 alerts because we are quite big networks, and we have a reactivity to gravitational wave alert about 50 minutes in minimum, and that's very, very low compared to the other one, because you can imagine that if you have 1 telescope at a site, I don't know, in USA right now, and it is daytime, then you will not be able to promptly observe after a gravitational wave alert. So we did not find any counterpart, if it is a suspect, during the O3 campaign, but the other groups internationally did not find. In fact, is much more harder than expected. And so that's why you need that this kind of initiatives needs to be more robust and more done more routinely, and also the participation or additional observation with the amateur observer. I just check the time. Okay, all right. Okay, so this is what I said. So now I would like to give some perspective about what we will do next. Okay, let me. Okay, so the last O3 campaign finished in March 2020, and the next campaign for gravitational wave counterpart hunting will be start about 2022. So what we are going to do between from now to 2022. And so our idea is to reinforce our skill from our networks of grandma, but also use that reinforces the skill, which means also observation, with other programs connected to the LabEx UnivEarthS. And so this include high energy neutrino from IceCube, led by Thierry Pradier. Also SNU alert, you know, the alert that can be emitted if there is a galaxy supernova around. Also practice on gamma ray bursts, and also practice on maybe Kilonovae that have been found with optical survey, either via the thing that you heard about it, I think today or yesterday, but also orphan Kilonova, especially from ZTF. And so with the observation in 2021 on all these different other alerts, connecting or not to a messenger alert, we can still practicing on our tools that are used for the professional, but also for the amateurs, also tackle the problem of rough localization of the sky, especially with high energy neutrino or SNU alerts, everything that is connected to neutrinos, in fact. We practice our photometric tool because, as you may understand, if you have a network with these such diverse telescopes, they have different filter, etc., etc., and we need to adjust the different photometric point to have a very good light curve, for example, attached to the event, so that we can practice with orphan Kilonova candidates on gamma ray bursts well localized, and also to observe other alerts during 2021, help to still make the collaboration alive and test practice all together, as well as integrating new groups. So as I said, this training that is also science during 2021 and 2022 is also to reinforce a tool that we develop within GROMA, and we develop like freely. We never have some money to do that because GROMA is not a CNRS, let's say, official program. It's based from bottom-up researcher from different institutes, but somehow we have developed many tools that are publicly, so it's on the Git and it's public, and all the, to be honest, all the consortium also use our tools, so we are quite proud of that. And there are still a lot of large involvement of from the scientific part in 2021, included APC. But it's true that since the GROMA is not an official program, we are lacking on technical engineering support from CNES engineer, and this affects a bit the project. Well, affect a lot, but we try to find a solution. Also, to face on 2022, because the gravitational wave detector will be much more sensitive, then the telescope should be much more sensitive, because you will see farther away, so the Kilonova will be fainter, so you need to have telescopes that are much more sensitive. And that's why in GROMA we try to find some we try to think about some dedicated programs for survey the sky, especially for gravitational wave and neutrinos. And so we think about this kind of 80 centimeter clad that can be installed in different observatories in GROMA under the in professional sites. And there are some of the groups that have the money for that, so we are quite happy. But I talk about that because we need to test new camera, and etc., etc. We're gonna to make a campaign of this camera characterization for this kind of telescope that I call Eurovision Transient Facility within January. So upgrade also on the telescope sensitivity and on the telescope network sensitivity. Finally, because we have included a much more team that maybe were not tackled with any gravitational wave astronomy in their country, we were obliged or not obliged to really monitoring these countries and also monitor the astronomer amateur because it is kind of the same. And that's why we try to develop also freely some pedagogic initiative. So for example, on our grammar website, we have some kind of explanation about what is grammar in different language. We also have a YouTube channel when we have different scientific seminars. So it's much more higher, I'd say, and a quite educational seminar, but you have all the environment about multi-messenger ecosystem, etc., from our competitive group or from colleagues. And also, I just want like to highlight the wonderful work from the Azerbaijan the room that's because of Grandma, she started at the first time an Azerbaijan website about gravitational wave astronomy and even astronomy in her country, and she tried to traduce everything to Azerbaijan, to Turkish, etc., to drive the science into this Middle East country. Okay, so just maybe I try to finish. So we have also, thank God, a little money from University of Paris to press ahead this citizen science program, especially the platform, because when the amateur observe them, they need to upload their data on a platform, and so we will develop that under the University of Paris. This project started, we have the developer, and we will do that to have a platform ready for gravitational wave, but also neutrino, etc. alert for 2021. And we hope to also be at the Rencontre Ciel Espace, representing APC and Université de Paris and our project, if COVID allowed in spring 2021. So voilà, so this is my conclusion. So our project is really focused on multi-messenger. It started from Kilonova hunting connected to gravitational wave, but as you see, there is such an excitement about grammar, collaborating all together, all the observers together, as a professional and amateur, so that we are extending the program now to neutrino and optical survey and gamma ray burst in the next year. So thank you, and I'm happy to answer to the question.
Thank you, Sarah. Is there some comments or questions? Don't hesitate to raise your hand. Okay, so if there is no question right now, I will ask a question. How do you meet new amateur? Is there some dedicated network to find some new people to participate to the program? Or
I think it's more or less bouche à oreille, more or less, you know, the when we make first a call to the radio to ask them, then we have this. Yeah, we have some paper into the journal, and those that help, but we don't have a systematic search from amateur. We should do that, but it's clearly not a top-down that we, systematically find all the clubs in France or abroad. I know that there are some amateur, for example, that were part of variable star hunting or variable star, and so they redirect to their community. So it's bouche à oreille in some sense.
And do you have some demand from this club or to have some teaching or trainings?
Yeah, exactly. That's why I highlight the Pédagogique, because in fact, we tackle a certain category of amateur that are very already kind of non-professional amateur, but they are very from the elite or éclairé. And so they really would like to know about the photometric, how to do the photometry on their own. Some other wants to know everything about gravitational astronomy. And so sometimes I redirect to the thing that we do at APC or LIGO, Virgo especially. But they would like to teach that, and they would like also to teach, and this is our thing that is the piece, let's say, la pièce qui manque, sorry, I'm a bit tired, but about the how to observe this transient. And it's not like Virgo that have this kind of thing in hands. In not the work that we do, at University of Paris, APC, to provide this kind of tips. So this is the work that we try to do. But that's why we would like to organize somehow a school or meet them at Journée Rencontre Ciel Espace to really try to drive this. But this is the thing that, that is missing, but is exactly the same for let's say, the countries that were not doing gravitational astronomy before. So it's strange, but finally the non-professional and some of our group that have a telescope, they have the same demand for us, and it is really pedagogy and practice and pedagogy. Practice, pedagogy, practice.
Okay, thank you.
I would like to say something. Thank you, Sarah, for your presentation. And I just wanted to underline the comment from Lorfalo, who says that Grandma is a great name for a citizen science project. And it just, so I just want to ask you, where did you find this name, and what's it important for you to have a good name for your project?
So Grandma is really like kind of collaborative. I say all aboard, but the name was found by not by me, but by my niece person, Observatoire de la Côte d'Azur, and they really like to say, okay, let's say multi-messenger addicts, because this is that we wanted from the beginning to include amateur and so on. So we say, okay, why not about multi-messenger addicts? And we like the grandma because for me it's like taking care of all of us, taking care of whatever, and driving diversity. For me the things is diversity. So that's why we use that name, and we like it. It was a bit how can I say, the only problem with this kind of name is that when you type grandma on Google, you don't reach to the grandma project first. You need to say grandma telescopes. But if we become very popular, maybe we will be at first on Google. I don't know. So this is the only problem on this kind of funny name.
So you have to spend part of your money to grade in the Google.
Yeah, I know that some of them they complain about that, and also it was funny because a German, he said, "Oh no, but grandma is the bomb or something like." Gross. So everyone, I think grandma is a problem on this kind of name, but it's I think it's funny. I think it will be fine.